welcome back. We've reached my favorite section, 6.1, which has to do with using integrals to find volumes of three-dimensional shapes. This first problem, part 1a, says the base of a solid is the region between the curve y equals 6 square root of sine x, which I have written here, that's this graph. So in other words, this is the x coordinate, this is the y coordinate. And the problem states that the cross sections are perpendicular to the x-axis. So the cross sections are perpendicular to the x-axis. And it wants us to find the volume if equilateral triangles with bases running from the x-axis to the curve, as shown in the figure. So the idea of what we're doing here, like if I wanted to draw this shape in 3 dimensions, it would probably, I don't want to ruin the drawing, but it would probably, it would look something like this. It would kind of, almost like a, kind of like a banana. It doesn't really matter. It's just good to visualize what this thing's going to look like. And how we're going to do that is we're going to use little tiny slices of equilateral triangles. And we're going to sum those equilateral triangles from x equals 0 to x equals pi. The first step, because we're looking for volume, the first step is to find dv, which means a small chunk of volume. And we've kind of already decided that we're going to integrate with respect to x. So this little infinitesimal is going to be called dx. And then I'm going to draw this equilateral triangle so we can figure out geometrically what's going on. So I didn't do the best job there, but with an equilateral triangle, all the angles are 60 degrees. And all of the sides will be the same length. I'll call it L. And with a triangle, to know the area of a triangle, we need to know its height and its width. And we already know its width. Its width is L, so we're trying to solve for the height. Well, we can do that by drawing a line that's parallel to this lower part of the triangle. And then we can draw a line up from this edge, and we'll find that we have a right triangle. Well, we know that this is also a right triangle, and so 60 plus this angle must be 90, so this angle is 30. And 30 plus 90 plus whatever must be 180, and that whatever happens to be 60. And we're curious about the height, right? The height is over here, h. Once we know h and L, we can figure out the area of this equilateral triangle. So h is going to be, this side's L, right? It's also the hypotenuse of the right triangle, so L, L, L. Well, if that's the hypotenuse, then we should be able to say that h, so remember, opposite over hypotenuse, h over L, equals sine of the angle 60. So if we look at the angle 60, its opposite is h, and its hypotenuse is L. So opposite over hypotenuse equals sine 60. We can rewrite that and say that h equals L sine 60. And we know that sine 60 is root 3 over 2. So h equals root 3 over 2 L. And then we also know that the area of this equilateral triangle, like all triangles, is equal to 1/2 base times width, which in our case the base is L. I'm sorry, 1/2 base times height. The base is L and the height, the perpendicular height is h. So 1/2 L times h, which if we write this out further, we'll notice that we get root 3 over 2, so we get 1/2 times L times root 3 over 2L. And what we end up with is area equals root 3 over 4 L squared. Alright, so that's the area of our equilateral triangle. But we're looking for dV. We're looking for a small slice of volume. Well, to have volume, we need to have some depth. And as you see right here, our dx is our depth. So in other words, these equilateral triangles have a little bit of depth to them. Kind of imagine that. And the width of the depth is going to be our infinitesimal dx. It's with respect to x. And so if we want to find dv is equal to the area of our triangle times its width, which is dx. So dv equals a dx. We know what a equals, so dv equals root 3 over 4l squared, root 3 over 4l squared dx. Alright, so that's our dv. Now if we integrate our dv, so in other words, if we take the integral of dv, we will find the full volume. Because if we add up all of these volumes together, we're going to find the full volume of this odd shape. And so the trick here is to find how to write things differently. So you'll notice the L on here, I've got it written as L. Well, how would I relate L to this graph? Well, this is my x-axis and this is my y-axis. I know that L indicates this distance right here, which is the perpendicular distance from the x-axis out. Well, that's also the y-axis, right? And if I plugged in, for example, if I plugged in sine of pi halves here, I would get 1. Square root of 1 is 1. Times 6 is y equals 6. So when x equals pi halves, which is right here, y equals 6. So that means that at this point, right in the center from 0 to pi, that our L equals 6, so does y. So using that substitution, we can rewrite everything with an L as a y, because no matter where you're at on the x-axis, your y-axis will represent, of your graph, will represent the length of the equilateral triangle. So we can replace this here with the square root of 3 over 4y squared dx. And I'm summing all these triangles from 0 to pi, right? Those are my boundaries from 0 to pi. And that's with respect to x, which is really important. We have a dx, therefore we need to find our boundaries in terms of x, because we're integrating with respect to x. It also means we're going to have to figure out what y is in terms of x, or more rather, y squared in this case. So let's take y squared. So we're just taking our function y and we're squaring it. 6 squared is 36. Square root of sine x is just sine x. So now we can multiply this in here, and what we'll end up with is we're going to pull out the constants out from our integral. We've got a 36, a root 3 over 4. We're integrating from 0 to pi. And then y squared is equal to 36 sine x, but we pulled out the 36 already. So it's just equal to sine x dx. So now we have everything in terms of x. We know how to do this antiderivative. The antiderivative of sine is negative cosine. So what we end up with is negative cosine of x. We're evaluating that from 0 to pi. And then we're going to multiply it by 36 times root 3 divided by 4. And to simplify, 36 divided 4 is 9. So we're looking at 9 root 3. 9 root 3. I'm going to make some room here. Now we've made it through here. And we're very close to the end. So this is going to equal 9 root 3 times negative cosine x when we plug in pi, so negative cosine of pi. And then we're going to subtract when we plug in 0 for negative cosine, so negative cosine of 0. And we're just about done. Cosine of pi is negative 1/2. Negative 1/2 times negative is positive 1. Cosine of 0 is a 1. So this is 1 minus a negative 1. That's 2. 2 times 9 root 3. 2 times 9 root 3 is 18 root 3. And at that point, we've taken our concept of this equilateral triangle, this small chunk of volume, and we've summed all of those chunks of volume together to find the true volume. And in this case, it's 18 square root 3. So there is a part B to this problem, but it's the same problem, you just do a square instead of an equilateral, and that'll be good practice to figuring out how to set these up geometrically. Alright, well I hope this was helpful, and I'll see you next video.